I never know when I'm actually streaming. Right. Just double check. And it says I'm live. I just got the little ding from LinkedIn. Hey, everybody, we are going to start the program. We're going to be talking about arc flash and incident energy. I got Mike King waiting in the wings. He's getting ready, getting all this good stuff going on. And we're going to get our butts together with regard to talking about arc flash, incident energy, and everything there is to know about from a theory and from IEEE 1584, NFPA 70E. I got my 70E book. I got my IEEE 1584, both the 2002 and the 2018 version. So we are going to get this ball rolling. And I think Mr. King, whenever he gives me the thumbs up, and we are ready to go. And welcome. Whoa, hold on here. That didn't work out too good, did it? Hold on. Let's just let me do this. What the heck? Let's figure this one out. Guest one. I lost MS Teams. Let's just do it this way. I'm not sure what happened on my end, Michael, but here I was. I got to do display one. So hold on. There you are. Well, see, everybody gets to see production in work. So we are live, and everybody gets to see exactly how I put these programs together. And this is what live means right here, brother. This is live.
On my end, switched rooms on you in the last 2 minutes before the presentation.
No big deal. No big deal.
And here I am trying to turn my books around so I can read right side up.
Beautiful. That is what being live is all about.
Love it.
Love it. This is good stuff. So, thanks for coming back, Michael. I know, or Mike. What do you prefer, Mike or Michael?
I don't really have a preference, but when I joined the training group, there was another Michael Sprague, and he was Michael.
Okay.
So I became Mike.
Okay. All right, Mike. Or Mikey. Mike. Just Mike.
we won't go to nicknames here.
Yeah, that's right. So I just got a note that said, okay. So James Smith, thank you, sir. It said at first it didn't seem like we were live on YouTube. So we're live on YouTube, and it says we got people watching on YouTube, Facebook, and I know I got LinkedIn. Welcome, Mike.
Oh, thank you. For this one, Tom, I even rolled up my sleeves here.
Yeah. Oh, look at you.
We're going to dive into these calculations, and I know this is going to get rough.
Losing the tie, buddy. I'm losing the tie because we're going to get down with it.
I love it.
Okay.
Yeah, no, I mean, this is a great topic. I know I had a post earlier today that said, hey, reach out with questions. I saw that you were on LinkedIn active today asking for questions.
Yep.
Questions came in, and I'll tell you, I was at about 4:00 today. I was frantically Googling, right? That's the proper term. Googling answers for everybody. Because Louis Montoya messaged a question, and I didn't even know what the acronym stood for, nor less what he was talking about. I Googled the acronym, and sure enough, I found out exactly what he's talking about. And I said, wow, I learned something new here. Makes perfect sense on what we're talking about, and that was BESS.
BESS.
Yeah. Do you know what BESS stands for?
Better eat spaghetti soon.
I love it.
Yes.
I love it. That is not what Google said. And I got a piece of paper here in front of me because I want to get this right.
It looks like an IEEE paper.
It is an IEEE white paper. You're correct. It is for The battery energy storage system.
Ooh.
So the question was around DC arc flash calculations. I also learned, do you know what FES stands for?
FES. Fault.
FES.
Factory.
No. Flywheel energy system.
Flywheel energy system.
And then we got CAES, compressed air energy storage.
Okay.
And SME, superconducting magnetic energy storage.
Wow.
New terms to me. Yeah.
This is good stuff. So we got Ryan Jackson in a hotel room in Alabama. We're being rebroadcasted, Mike, over the Wisconsin IAEI Zoom meeting. We got Jindang. So Jindang, where are you out of? You got to let us know where you're calling in from. We got David Englehart. We got James Smith, Chicago. Gustavo Chavez. So
awesome.
And he says, "Pop the clutch." And we got Dawn Ganir in the house. So this ought to be a really good program. So looks like Star Trek discussion. Kevin Breen. Thanks, Kevin. Wow, we got Tamaki Ono from Japan. Ahmed, I believe that is Egypt. Richard Curran, boy. And we got Calgary, Canada in the house. Okay. All right. So, Mike, how do we want to start this? I know. Why don't you do this? Why don't you give us your background again on what you do from an Eaton perspective, and then we'll just dive into arc flash calculations.
Yeah. So I will say I think I shocked you last time I was on, because after we were off the air, I gave you a heads up and said, Tom, I'm changing roles, and you lost it. Right? Thankfully, you were not live at that point. I've actually now taken a position as the team leader for external training for EESS.
And what is EESS?
That is the Electrical Engineering Services and Systems Division. It's technically EESSD, or division of the electrical sector within Eaton.
Awesome.
So we're a separate division from the manufacturing side of the business. And our division is responsible for providing those services to our customers, such as startup, commissioning services, preventive maintenance, power systems engineering studies. Cool. We have control engineers, automation engineers, as well as retrofits, retrofills, and all the updating of equipment over time, including PBRCs, power breaker centers.
That's right. In fact, who was it? We're going to have to do a whole series on retrofitting and retrofills. I remember your email. I got to follow back up, because that ought to be a really good program to talk about what you can do on existing equipment.
Yes, absolutely. So I work for the training group that has to ultimately train on, all of our employees to provide those services.
Right.
But also we provide training to our customers on those services. So, one day I might be talking arc flash. The next day I'm talking about, testing of breakers, to, the theory on how stuff works. How do we do, we're going to talk about short circuit calculations.
Right.
We have classes on that. So, wide spectrum of classes that we can instruct on different topics. And that team that does the external training part ultimately now reports up through me. So we're going to get some of them on this Tech Talk here in the future for sure.
Excellent.
And show you that it's not just me, that there's a whole team here to support you.
That is cool beans. Thank you, Mike. Okay, so when we think about arc flash calculations, and I mentioned this morning because technically I should have taken for my whole electric, from a safety May being safety month, right? I should have started with the single line diagram, moved into short circuit calculations, moved into selective coordination studies, and then did incident energy, because that's the order. You need a good one-line diagram, right?
Yeah. I mean, if you don't have that one-line diagram to define what your system is, you can't do these calculations. You can't get to that point. So yeah, it really is the starting point, and you know, there are facilities that have really awesome and great one-line diagrams. There's lots of facilities that don't. Some are drawn on napkins.
Yeah, I know. I know. I've seen the napkins. I might have been a victim of the napkin syndrome, or maybe a contributor to the napkin. We're all engineers. Just that's what we do.
Mm-hmm.
If there's a napkin on I mean, I can't tell you how many. I won't say bars. How many restaurants I've been in where we use the napkin. So I we use the one-line diagram for short circuit coordination, load flow studies, and we say safety evaluations because we use these one-line diagrams for lockout tagouts. And I did a whole program on the one-line diagram. I think I have multiple instances of that, and it just can. I can't personally stress it enough on how important that single line diagram.
Mm-hmm. Yeah, and let me just add a little piece there. It really even goes beyond the one line diagram, I think, in a lot of scenarios. When you start talking about the clearing times of protected devices, that information isn't necessarily always shown on the one line. What are all the settings of your breakers? What
Oh,
are the
yes.
CT ratios, right? All that stuff. So the one line is kind of the starting basis, but it really goes beyond that. And then, it goes into your three lines. It goes into your wiring diagrams, how the system's actually connected. One of my favorites is, and I know we're gonna bring this up later, is traditionally we look at protected devices clearing based on fault current.
Mm-hmm.
But that time current curve it's not the only way a protected device senses that abnormal condition and decides to trip, right? So we can talk about ZSI, differential speed.
That's right.
It can all feed into this.
Yeah, you're absolutely right. And we don't talk much about the three-line diagrams. I think three-line diagrams are more used in medium voltage applications than the lower voltage, but that's and the three lines are going to show you your CTs, where they're at on either, like if they're on both sides of the on different sides of the transformer, or if they're in a motor or whatnot. Yeah, that's a good point from that perspective. I'm going to just do something here because I don't know where this is going to pop up, and I have a fear that it's going to pop up. No, okay, good. I thought it was going to pop right over your picture, but all right, so I've got both of the standards open, and let me do this. So I got both standards open. I'm going to put that over here because we're probably going to be talking about this. So the fault currents. Let's talk. So we understand the one-line diagram. One-line diagram is going to tell you all of your different sources of power, what's going to be paralleled, where your motors are. Motor contribution is important for fault currents. What motors can be on, off, all that good stuff. And to your point, a one-line diagram is not going to have the settings of the overcurrent devices. So like, for example, if I have an electronic trip unit that is, say it's a 2000 amp circuit breaker, and I have an electronic trip unit, I have a long time delay, long time pickup, short time delay, short time pickup. I have an entire trip curve and all the settings that are rarely on the one-line diagram. That's usually where? In the coordination study.
Normally, yes. They could be on the one line. I've seen it done before, but it's not necessarily common.
Yeah, because that's a lot of that's a lot of information, depending upon the trip units, right? Obviously, because because you could have long time pickup, long time delay, short time pickup, short time delay, instantaneous pickup, and then you can have ground fault, right, as well. And if there's an arc reduction maintenance switch, what it's set at. Santiago, good afternoon. I don't know what else. I mean, you have like 7 different set points. Plus
DSI.
Well, yeah, then you have to know if it has ZSI. So it just gets really complicated. Now, how we do that typically on one line on diagrams, as you know, like panel schedules, we'll have a whole set of panel schedules, or we do it in the notes, right? we'll publish notes on the drawings, because that drawing is a living document.
Mm-hmm.
So, okay, so you got the one line diagram. Then we get into the fault currents. And if you think about the calculations, IEEE 1584 is typically, I mean, that's what we're going to use when we're calculating incident energy, and it begins with the fault current. You need to know what the bolted fault current is that you're going to calculate, right?
Yes.
And let's just talk a little bit about, let's talk a little bit about the calculation itself. I mean, we say we need one of the input values to an arc flash analysis is the bolted fault current, and then it will calculate a minimum and an arcing current and then a lower arcing current, right? So it gives you that range. But the fault current itself, I can configure my one line. I could turn all the motors on and get a fault current value, turn all the motors off, get another fault current value. One's going to be greater than the other. And we know that a higher fault current can give me a high incident energy, and a low fault current can give me a high incident energy, right? So, I mean, I would think that somehow you have to configure the system both ways to get both of those numbers. And then really you're going to have like 4 arcing current values, one at the maximum, one at the minimum. I would think you'd have to do both of those, wouldn't you?
Yeah, you would. And it can actually be worse than that, really. So if you think about a double-ended system where you have 2 main utility feeds into the facility, right? Those 2 utility feeds may actually have different fault contributions.
Yeah.
If they're fed out of the same utility substation, the lines are going to be the same distance, same size, as you would expect that fault contribution to be about the same. But if they're now fed out of 2 different substations, we now have different impedances in the lines, different lengths, etc. The fault can change. So now I don't need to just consider all of my calculations based off of min and max for one utility feed, but now for the other utility feed. And if they're able to be synced, they are synced. Now I have to look at a combined utility fault situation. So when we're talking about running of scenarios, I'll tell you a quick little story here. Years ago, I was I was doing an arc flash study for a customer of ours when I was in the power systems engineering group, and that customer then came back and wanted an update to the study for some changes that had taken place. And I quoted a price and said, yeah, I estimate here's how many hours it's going to take. And they said, Mike, come on now. We know you put some stuff into this computer program and you hit the go button. And the go button just calculates everything for you and we're good to go. But, that software is written by humans, right? We make mistakes as humans, right? And I potentially make a mistake entering data on all those fault contributions. So the process here of doing a study is really reliant on that engineer or that person performing the analysis to take into account all those different scenarios, because that fault current is going to affect the arc flash incident energy.
Right. And it's really about the relationship of the current to the trip curve.
Yes.
Okay. So if I take a look at my configuration and I have a maximum available bolted fault current where the minimum arcing current is in the instantaneous region, down there at a very fast clearing time, if my minimum and maximum are in the same clearing time, then my higher energy will be based upon the higher arcing current, right? Because it's the same clearing time. But if I reconfigure my system in a realistic manner that, say, I don't have any of my motors running, and I'm on to your point, the utility feed that has a lower available fault current, now my minimum arcing current could be in the short time delay region or even the long time delay region, and now my incident energy goes through the roof. So the more complicated a system gets, the more configurations you need to compile to make sure that you establish what is my maximum and what is my minimum. And your study, if you make assumptions, for example, if you sat down with the facility owner and you were looking at all of the motors in the facility, it would be probably ridiculous to say at some point no motors are running, but you have to come up with what is the number that you use. Is it 50% of the motors running? Is it 20% of the motors running? And I think the only way, I don't think you're going to find an IEEE study or a document that's going to give you that number. I think you need to figure that out based upon the conversation with the customer, right? Talking to the facility owner and looking at the processes, or if you're in Canada, the processes, right? And then figure out what is a realistic number of like these motors are going to be on, these motors could be off, etc. And then you calculate those numbers. And then if you have double-ended switchgear, multiple utility feeds, and then if you have a generator too, right? So if you're going to run a system off a generator, it's going to be even a lower current, or could be.
Could be, and I'll throw another scenario in there. What happens if you have backup power because you actually have really, in essence, you're building a microgrid, and that power source is now actually solar array.
Yeah.
And the fault current off of a solar array is completely different compared to a fault off of, say a generator or the utility, how it reacts in a fault situation.
But here, yeah, so here's the thing, and Santiago brought this up in one of his questions too. And he's saying, what about solar panels or distributed generation, in which we can't certainly know which ones are connected to the grid? And now here's my issue. If I have, like on a variable frequency drive, let's say that I have a motor, and let's just use the VFD as an example. I have a motor that's being controlled by a VFD. If I have a fault on my power distribution system, the VFD doesn't push the fault current contribution from the motor, right? Because the VFD is going to basically, it's controlling, and it sees a fault, it shuts things down. Now, it's like if you and I are having a personal conversation and we're in the cone of silence, but I can hear what's going on behind us. I don't let your conversation go up there because I'm controlling right here. Okay. Now, and Richard Curran makes a good point that you could have VFDs in bypass mode, right? And then you have to make that assumption that they're in bypass. But if you don't have a bypass mode, my point is you have an isolation. And I'm wondering if inverters do the same thing.
So my understanding of inverters, Tom, and if there's anybody out there that has that expertise that wants to chime in, feel free. My understanding is even in a fault situation, the inverter is still going to feed the fault because it's a normal source of power. It may not increase the current in the fault, but it's still going to provide that load current baseline at least.
Right.
And I want to say, if I remember right, and this has been years since I've done studies as a career, I want to say, for one of reason, 30% above full load is what's sticking in my mind, but I can't tell you why that is, Tom.
No, you're right.
So
you're right.
don't quote me on that one.
Nope, you're right. And what does NREL? NREL, I believe that's National Renewable Energy, not laboratories. Is it laboratory? NREL? Yeah, National Renewable, I think it's a National Renewable Energy Laboratory. But I think they had published something on this. I'm looking for it right now in regard to the fault contribution of inverters, because that's what there's going to be a maximum that it can put out, right? And we know that you're going to have a maximum amount of energy that it can deliver, and that's what you would assume, right? Now you could also assume that it's not putting out as much because I believe it's going to depend upon what your solar array is doing too, right? So you're going to have those, but so you've got to think about all of this when you're coming up with your fault current values, and you're going to need a maximum available fault current and a minimum available fault current to really come up with the right arc flash energy because you just need that lower number. And it could be that, if you're looking at the 30% or whatever it is from a PV, contributing from a PV inverter, or if you have bypass on some of these VFDs, do you assume bypass on all of them? Do you say, I would never have all of my VFDs in bypass mode? Is that an unrealistic? So these are judgment calls. These are all assumptions that you need in your study.
Yeah. Can I complicate it a little bit more?
I don't know if you can throw.
Do we want to?
This is like my cousin Vinny. What more can we throw on here?
Well, so I have a IEEE standard open on my computer right now.
Okay.
Because somebody was asking this question, and I don't know how up to speed on all the standards you are, Tom, if you know the generic name of this, but it's the IEEE standard 242.
Oh, I know that one.
You know that one, right? The Buff book.
Right.
The Buff book is our guidance on how to do these calculations.
Right.
Let's throw into the fact that we've been talking about stable fault currents right now, but not all these sources are actually stable, right?
Yeah.
They change during the fault. So when we talk about like motor contribution, say induction motors, they're only going to contribute to that fault 3, maybe 5 cycles with significant current.
Yeah.
But my clearing time based on all these currents is going to be 2 seconds, maybe a second and a half. Now I actually have to deal with multiple fault currents and times to figure out my energy and somehow add them together.
Yeah. So your study, if I'm going to do an arc flash study, and it can get complicated. That's why I'm saying in heavy commercial or heavy industrial, I will say commercial buildings, your light commercial buildings can be very simple. I mean, you have a single service, you have a couple panel boards. That is relatively easy. The dynamic that you have there is, if the utility gave you a fault current value and said this is based upon an infinite bus, how do you get the lower, the actual fault current? So that's typically where the challenge lies, is you're working with the utility and you're saying, hey, I need the available fault current. It's really important to tell them. Now, I've talked to Alabama Power, I've talked to I believe it was AEP, Georgia Power, and a few others, and they said, you got to tell us that you're doing an arc flash study, because then they'll have to put some more effort to give you a more realistic number that's not based upon an infinite bus, which is based upon the lowest possible impedance that they could possibly buy from us, right? When they buy a transformer from our Cooper side of the business. And so, because typically we're worried about interrupting ratings, so they're going to give you this artificially high number so that you don't have a problem with your equipment from an interrupting or SCCR. You need that lower number, that more realistic number. I mean, have you run across any issues? Like, how do you handle that? I mean, I know we have an IEEE paper on this discussion, but your thoughts on that one?
So Tom, I have a story for everything, right?
Yeah.
So I won't tell you where it was at, because that would give up the utility's name, and I'm not going to do that.
Uh-huh.
I was doing an arc flash study back in those days, and I asked for the utility fault contribution, and at the service entrance of the facility, and the utility came back and said it's 200 kA fault current. Okay. I'm like, wow, pretty impressive, right? And but they didn't tell me if that was on the primary side of the transformer or on the secondary side. I didn't know what voltage level that was at. So I asked them which voltage level that was at, and their response was, it doesn't matter. because their quick, easy answer to that question of what's the fault current is it's 200 kA because that's the highest rated equipment anybody makes. Yeah. Doesn't matter what voltage it is. That's it. And so as individuals perform these studies, that data collection piece, like you were saying, figuring out which motors are on, which motors are off, what those normal situations are, source wise and everything, and then okay, is it interlocked? Do we have to have synchronization? Right. Can I run this stuff together or not? That's all important. Utility information is another critical piece of information you need. And that's where you want to have that good relationship with the utility and say, I'm doing an arc flash study. You know, people's lives are dependent on this. Right. And I think times are changing. As I've seen over the years, I think utilities understand that more than maybe 10 years ago. Mm-hmm. And they're more willing to give that information up. You know, with I think the clarity of this information is valid for right here, right now, as we do the calculation. Next week, a change in our system may change that value.
Yeah, and I agree with you that utilities are understanding this. That's why, like I said, I've talked to Georgia Power, I've talked to Alabama Power and AEP, and those guys. And I was doing presentations and educational programs, and they're in the audience, and they stood up and they said, "I got to interject because they want to make sure that people knew to tell them what you're doing because they'll give you that other number, which will be a lower number than what they assume up here, because what they'll do is they'll say, like what they do now, if they assume an infinite bus, they'll assume an infinite bus with the lowest impedance of the transformer. But if they know that what you're doing, they'll give you the number with the highest impedance of the transformer, and then you can take it from there so that at least they have that covered, that complete bandwidth. Because, and I did a program on this where I showed that the source impedance, the Thevenin equivalent, looking up into the system, when you have that big hunk of iron of a transformer, you can widely vary the available fault current on the primary of that transformer, and you really don't significantly impact the secondary as much as you would think. So they can, with a level of confidence, know their range of fault currents is not going to impact the secondary, and understanding the fact that there's a maximum impedance and a minimum impedance when they buy a transformer, they can get you very comfortably into that range of, well, here's my maximum and here's your minimum fault current that we could possibly deliver to your service. Now, we wrote an IEEE paper, and I should have it. I can't remember who it was, and I know the gentleman is Greek from up there, and he's got a name that's like 3 miles long. It's almost as bad as Dimitrovich. It's Kalakalakalakalakalis or something like that.
Is it really Greek?
Yeah, he is. Yeah. I gotta find it. But in any case, they wrote a paper based upon they looked at a bunch of different studies, and the utilities, initially given numbers and then subsequent numbers, and what they learned was that lower number is worst case 50% of whatever that higher number was. So the thought process and that they delivered in that IEEE paper was, whatever the utility gives you, if they don't give you the number associated with an incident energy, available fault current, short circuit, the lower short circuit current, just take that fault current. If it's 150,000, cut it in half, and now you have your maximum and you have your minimum. And I know we have a link to that on our website. And I got to find it. And when I find it, what I'll do is I'll post it on this link. I know I have that. So that's the fault current from the utility.
Yes.
In a commercial building, a light commercial building, that's really, the motor contribution is probably very insignificant just because they're smaller motors. there'll be a blip on the fault current, not as significant, unless you're doing I learned a car wash station. Motors can be significant. Okay. I learned that one during a presentation. But so your light commercial projects can be very simple, easy, straightforward. Your heavy industrials, where you have multiple, like you said, double-ended. I went to Schriever Air Force Base one time, long time ago. And I was all excited about, I'm going to an Air Force base. I'm like, what fighter jets? I was Googling, I was researching fighter jets and their profiles, because I was like, if I see the profile, I want to be able to say that's an F-14, that's an F whatever, right? Or whatever it is. And I showed up, they came pick me up, and I go to the site, and I'm like, there's no planes. And he goes, no, we don't do that at this Air Force base. I'm like, you're not an Air Force base if you don't have planes. And what they was the command central for a lot of our military operations globally. And they had what they called pods, okay? And every pod was like a computer-based system, and they're looking at missiles, they're looking at all kinds of stuff. But then they had double-ended switchgear after double-ended switchgear after double-ended switchgear. They had big, huge rooms full of batteries. They had generators like you would not believe, because it's a critical installation from a national security and everything else. So it was a very interesting sight to see with regard to the amount of hardware, electrical hardware they had on site. That type of a facility, or a data center, those facilities can be very difficult to arrange your system to get the maximum and minimum fault currents. So just
yeah, I used to think, when we talk about power systems and keeping critical equipment up and running, I used to think hospitals were. But when you talk about, like you said, military complexes, talk about data centers, I got another one for you: casinos.
Really?
Oh yeah, casinos are huge on having multiple sources of power coming into their facility and backup after backup, because just simply because of, if the power goes down, think about the money that potential losses you're going to have just for an hour or 15 minutes. And now all those servers and all those machines have to reboot and everything, all the security systems, etc. They consume large amounts of power, and it's critical to keep them up and running 365. So yeah, lots of different sources coming in.
That's pretty good. Okay, so you have the different types, levels of fault current that you've got to think about, maximum, minimum, and rearrange the configuration. Now, once you get a maximum and a minimum fault current, then you're going to be using, now you're into 1584. Up until this point, you haven't even touched IEEE 1584. And what's the title of IEEE 1584? Is the IEEE Guide for Performing Arc Flash Hazard Calculations. Now, it was first published in 2002. And it took us 16 years to come out with the next revision. Okay? But the first version was the first time in 2002. That was the first time that we had a method to calculate arcing current and incident energy. Because we used other methods before. You had the Ralph Lee method, right? The Ralph Lee method came out in 1986, I think, somewhere in that ballpark. And Robert, good to see you, brother. Frederick Fowler says we got 28 pillar UPSs, 29 2750 kilowatt gens. That's insane. Frederick, you're insane. Man, that's like, I mean, that's think about that type of a system, right, Mike? So
yeah,
from 3 pages of formulas to 17, imagine another 16 years. That's exactly right. Right. So And believe me, with the way we work, I'll let everybody know about we're doing some additional testing as part of IEEE 1584 right now. In fact, last week we just completed some testing, and I'll let you know what's going on there. But here's the thing. So just talk about what we do from a 1584 perspective. We have what they call arcs in a box, right? You have a square enclosure. You put your electrodes facing down. We put a little guy wire, a trigger wire, I think they call it, in between those electrodes, right? And you know your available fault current at that piece of equipment. And then what we'll do, Dr. Lee, Dr. Lee will sit down, Matthew Hermison, Dr. Lee will sit down and say, we'll run a test and we'll watch the explosion, and we record the heat. We record the waveform of the fault current, right? And all that information. So Dr. Lee has the arcing current values, arc after arc after arc. We just keep doing event after event after event after event. And then we change parameters, change the available fault current, event after event after event, change the available fault current, do more events. And then what you're doing is you're creating, think about an XY axis, you're creating a graph of data points, right? And this goes right back to college. I mean, I can remember in random variables and complex variables and there was calculus, I don't know, it was either calc 1, 2, or calc 3, 4, or 5, or physics 6, 7, or 8, I can't remember, but we went through and figured out how to when you have a bunch of numbers on a graph and you draw a line across the top and you draw a line across the bottom, and then you had to come up with the equation form fitting. It was called numerical analysis. That was the name of the class. Right? It was numerical analysis. And I remember because I wrote a program for that. Now, it was a part of my senior essay. But you go through all of those derivatives and whatnot to come up with this long equation, which basically represents the curve. Now, what Dr. Lee did in the 2002 version was he calculated that top number. And then instead of coming up with an equation for the bottom band, all he did was he said if he takes 85% and he takes 85% of every data point, he encapsulates the worst case and the best case of the arcing currents, right? And the same thing with incident energy. So actually arcing currents. So he basically created one line in the 2002, and then we just took 85%. That's why when you sat down, you said you calculate the arcing current and you take 85% and you do, and now what you've done is you've come up with the worst, because there's no two arcs the same. You've come up with the band from an arcing current. It could be as high as this or it could be as low as that. And then you take both of those numbers and we did a calculation. But in the 18 version, he actually came up with an equation for the lower number. And that's why when, who was it that said, hold on. Yeah, Santiago Guzman says, went 3 pages of formulas to 17. And the reason that is because he's now calculating the lower arcing current instead of just doing 85%. So now here's the benefit of that. The arcing currents that you calculate based upon IEEE 1584 2018 are going to be higher than the 2002 version for the most part. And you say, well, why is that good? What does an overcurrent protective device like to trip faster?
Lots of current.
Lots of current. So the more current you feed an overcurrent device, the faster it gets, the lower the incident energy will be. Right? I mean, because it's a clearing time thing. If I have 10,000 amps and it takes 2 seconds to clear, as opposed to 60,000 or 100,000 amps and it takes less than a cycle to clear, I'm going to have lower incident energy with that 100,000 amps than I will have with the 10,000 amps at 2 seconds.
Yep.
So the higher arcing currents will get you into a faster clearing time than the lower arcing currents when you think about the an inverse time current characteristic curve of a circuit breaker.
Mm-hmm.
Go on here. And it really goes back to this, right? It goes back to this trip curve. If I can get my arcing currents into the fast clearing time, then I will have a lower incident energy. And if you look at the 2018 calculations, your arcing currents are going to be characteristically higher. I haven't done an analysis to see percentage-wise, though.
Yeah, I'm not quite sure how that works out percentage-wise, but yes. Yeah, so we did make it more complex in 2018. But I want to go back, just step back here a little bit and just talk about the progression, Tom.
Yeah.
You know, with Ralph Lee, that was purely 1980s, right? That was theoretical.
Yep.
So when we wrote the IEEE 1584, it's based on testing.
That's
right?
true.
It's based on real world, and I think you know, when you look at the engineering process, the scientific process, you analyze something, you know, you take your results, do that best fit equation, that best fit curve, right?
Yep.
Based on certain variables that you perceive to be important, really, and based on the data you recorded. But as you progress through time and you publish that information, people naturally come out and say, but Tom, did you consider the enclosure size? What happens if we change the box size?
That's right. Right.
Mind blown, right? We didn't think about that. Or I know we're going on this road, the electrode configuration, right? We changed that. It's not the same anymore.
That's right.
And so yes, the equations got a little more complex. There's definitely more of them, more calculations to perform, but we're trying to have a more realistic understanding of what's happening in the arc flash. Are we there yet? I don't know. Time will tell.
Yeah, exactly. And so when you look at this is an example of, they came up with VCB which is vertical electrodes in a metal box enclosure. Then you had VCBB, which is the vertical electrodes, metal box with an insulating barrier, right? And then they had horizontal electrodes. Now you remember that I'm sitting on my other end of my earbud. Remember that the arc always flows away from the source, right? So if I have this type of a configuration, my arc is going to, and my arc is down here on the bottom, right? My arc is going to follow those electrodes down, hit that barrier, and then project out. So the first step is you're going to calculate your arcing current, and we'll talk about what parameters impact that. And then you calculate your incident energy. And what we learned in these studies, Mike, was that the proximity of those vertical bus that is hitting an insulated end, and if it's close, which we really don't have a good definition of how close is close. So we're talking an inch, 6 inches, 8 inches. We really don't get into those details. That's left, you know what they call that? And I told Dr. Lee this the other day. I said, he made the statement. I said, so doc, that's left to the student. I heard that for 4 years of college. You know, they do the easy problems in class, and then the hard ones, they say those are left for the student.
Well, I have an answer for you.
What's that?
How far is that gap? It's 42.
42 millimeters? Inches.
Whatever unit you want,
There
42.
you go.
That's the answer.
42.
It's the meaning of life, right?
Perfect. So you have the arc, which will flow down. It will hit this and then bury out. So the incident energy that you'll get from a VCBB is going to be higher than what you'll get from a VCB because you don't have the barrier that's pushing it out.
Yeah, I agree with that. And I'm going to completely speculate here.
Yeah.
Because I don't know that there is test data. But my thought process there also is potentially because that barrier is there, that limits how far the arc can move away. Mm-hmm. Right? So that ionized gas stays there. Potentially that changes the resistance of what's happening and changes the impedance. And now we have a different energy calculation at that location. So how it all works, not quite sure. And I think that's the important thing. When you think about the equations from Lee, they were theoretical, right? If you didn't consider it, it didn't exist in those days, in that world, right?
That's right.
Now we're going off test data. We might not have all the understanding of why these variables are interacting with each other the way they are, but now we can start to say, based on the variables we have, this is what we're seeing as a pattern with the energy.
Right, and what we're doing, what Dr. Lee is doing in the lab is we're running tests because no two arcs are the same, right? And somebody in the testing last week, they said, boy, this is like looking at snowflakes because there's no two snowflakes that are the same, right? So all you can do is keep doing these over and over and over. Now you could, an engineer, a doctor of engineering could probably try to come up with models that would simulate the arc, okay? The random arc, simulate something that's random reliably is kind of a difficult thing, right? So, but what we did not do was we didn't rely on the simulation. We actually ran and did the tests, and then we created the equation based on the tests. To your point, what we used to do before 2002 was we only had IEEE papers. We had a lot of people who did their own testing, but we had the Ralph Lee method, which was based upon that engineering judgment, basically. But it was the best thing that we had. Mm-hmm. So then Richard Curran says, is there a way to calculate medium voltage transformer secondary incident energy? The spade spacing exceeds the allowable bus spacing parameters of IEEE 1594. So let's do that. Let's talk about what the limitations are of 1584. And I'm going to bring the 2018 version up. And it says in section 4, there's section 4 of 1584 is titled Model for Incident Energy Calculations. And it talks about 4.2 is the range of the model. So it says, the following empirically derived model based on statistical analysis and curve fitting programs, which we just talked about, the curve fitting, okay, is applicable for systems with the following parameter range. Voltages in the range of 208 to 15,000 volts. 3-phase, line to line. Okay, so that gives you the voltage range. If you're at 138 kV, forget about it. Okay, ain't going to happen. You're not going to use 1584 for that. If you're at 120 volts, forget about it. You're not going to use this. And the 120 volt thing, that's the testing that we're doing and we did last week. We're doing single phase testing now with IEEE with the same configurations to understand what happens on a 120 volt panel board. So, and I can't share any results, but that's the testing that we're doing, and we're not complete yet. And Dr. Lee has got to do his thing to come up with the floor, right? Okay, so frequency 50 or 60 hertz. So if you're at 400 hertz, ain't gonna happen. Voltage fault current, and this is the one that gets me, and we're gonna get to you, Richard, here in a second. Voltage fault current, 208 volts to 600 volts from 500 amps to 106,000 amps. Now, here's the thing, Mike. That's telling you that, remember, 1584 is the only document that I use to calculate arcing current, right? And it's only applicable up to 106,000 amps. 24087 of the National Electrical Code says, documentation shall also be provided to demonstrate that the method chosen to reduce clearing time is set to operate at a value below the available arcing current. So if I have a system, I'm in, I think he's, I think he's here. Mathur Abbasi, I think, is here. If I'm up in New York City and Mathur Abbasi says, well, we've got 200,000 amps or we've got 150,000 amps down at the bottom of this building, I can't calculate arcing current using 1584. And Ralph Lee method did not calculate arcing current. So technically, I mean, I've got to figure out, I mean, I have a method to be able to meet 24087. You calculate it at 106,000 amps. And just make sure you can trip on that, because can't calculate arcing currents greater than, when your bolted fault current's greater than 106,000 amps, from a 208 to 600 volts.
Right.
So, and then from 601 volts to 15 kV, it's applicable from 200 amps to 65,000 amps.
Now, I want to point out, Tom, this is one of those major changes in my mind. If we go back to the 2002 version, it only stated 700 amps to 106,000 amps, period. No voltages associated with it at all.
Oh, interesting.
Right? So there's a slight change there in where the model was applicable, that ultimately we were kind of ignoring voltage with regard to some of these currents early back in 2002, and now we're taking that into consideration.
You're right. You're absolutely right. But but you're right. Yeah. But here's the other thing.
Anyway, sorry to sidetrack you.
No. That's a good point though, because here's my beef. Here's my beef. 70E. You heard of where's the beef? I'm going to tell you where my beef is. 70E references the Ralph Lee method as an applicable method that I can use, right? And when do I use it? When does SKM, EDSA, Easy Power use the Ralph Lee method? When I'm above 106,000 amps and 1584 doesn't apply. So I did, you're going to love this. I did a quick, because when I was presented with the challenge, I had somebody call me, because I'm on panel 10, and I don't speak on behalf of NFPA or panel 10, but they said, hey Tom, I have an application where I've got 150,000 amps of bolted fault current. IEEE 1584 stops at 106,000. How am I supposed to meet 24087? And I was like, well, that's a good question. I can't calculate arcing current. So then what I did was I went to SKM and I modeled that scenario, and I put 110,000 amps and I put it on I forget what breaker it was, or a fuse. I think I used a very large fuse, right? Like a 4,000 amp fuse or whatever it was. And the large, or I can use like a Magnum breaker that is a double wide that has 30 cycles delay, get the same result. Mm-hmm. I ran the calculation, and the 150,000 or whatever it was, the bolted fault current was in the current limiting region of the overcurrent device, or in the instantaneous region. And Ralph Lee's method gave me, I don't know, say 8 calories. Okay. But if I made the fault current 106,000, or I made it 105,999 in SKM, the instant energy was 40 cal or higher, right? Because that even though the 106,000 was in the instantaneous region, the arcing currents we know are lower. And so I sat down and said, how can I take the exact same overcurrent device, put 106,000 amps in SKM and get like 40 calories, change the current to 107,000 amps or 108,000 amps, and the same computer calculation will give me, 4 calories or 2 calories or whatever the number was ridiculously lower. So how can I trust that Ralph Lee method at those higher values when it doesn't make sense? So I'm struggling with that, actually, and I'm not sure what the right answer is. My only answer for 24087 and 24067 was do the calculation at 106,000 amps because, and that's what the engineer who told me, he says, look, he says, I ran the calculation in SKM for this application. It tells me 4 calories. And I'm sitting in my mind, I know the overcurrent device. I know the arcing currents are less, and I know where they're going to be. And I know that number is way too low. And that's when I was going back and forth, and because he was going to tell the AHJ, the authority having jurisdiction, show him the arc flash calculation and say, look, I'm down at 4 calories. Go away, leave me alone. It meets the intent of 24087. And I think that's wrong because you're going to do a calculation. You've got to understand the arcing current's going to be lower.
Yeah. And I think, this is something I wanted to bring up on this call here. And I was going to bring it up for a completely different reason, honestly. But it kind of makes sense here. And I was flipping through my pages, so give me 1 second until I get back to the right page here.
Yep.
There we go. So when we look at 70E, 70E's requirement for an arc flash assessment, which is 130.5B, says the estimate of the likelihood of occurrence of injury, damage to health, and the potential severity of injury or damage of health shall take into consideration, the design of the equipment, the operating conditions, like we were talking. In A, under general, it says it needs to be performed. Really, 70E is saying you have to somehow estimate the energy, which is going to be the severity of the incident, right? If we receive that energy to our body. 70E in the actual standard doesn't tell you how to do that. They don't tell you 1584 versus Ralph Lee versus other methods.
But hold on. Mm-hmm. If you go back to Annex, hold on, let me get my other. I got to get both versions because we made some significant changes. We removed a bunch of equations. Annex D is incident energy and arc flash boundary calculation methods. Now, informative annexes are not enforceable. We know that, right? And that's where, and what it says, here's what it says. And I'm looking at my latest version. It says informative Annex D summarizes calculation methods available for calculating arc flash boundary and incident energy. It is important to investigate the limitations of any methods to be used. Okay? The limitations of methods summarized in informative Annex D are described in D1. In Table D1. I was like, I'm reading D1. And Table D1 talks about the Ralph Lee method, the Dougherty method, 1584, Dan Doan's arc flash calculations methods. So now here's the thing, Michael. So here's the journey that we take. Back here, to your point, we have the requirement. Back in the annex, it says, hey, by the way, here's what you can do. Here's what you can use. Now, Richard says, what about the median voltage? Because it exceeds the bus spacing parameters of 1584. So to answer Richard's question, what SKM does, what EDSA does, and Easy Power would do is fall back on the Ralph Lee method because it's outside of the parameters of 1584. And Ralph Lee did a great job in giving you this summary method that's based upon the bolted fault current value and the type of equipment, etc. and it'll come up with the incident energy value. But I already told you, I have technical difficulties with it. But it's the only other thing that we have. And what this really speaks to, Jimmy Dollard, Jimmy's IBW Local 98. And I remember back in the day, I would argue with him about the table method in 70E. Okay. And I would remember the table method in 130.7 Charlie 15A. It says as long as your available fault current's less than this number, and it says if it's this type of equipment, then here's how you dress. And I would go, the bolted fault current, I don't care about the bolted fault current, I care about the arcing current. And he would go, you're thinking about it wrong. And we would go back and forth over a beer. I mean, and it would get even more heated based upon how much beer or whiskey we drank, right? So it didn't click until I was in a different debate with somebody else about the Ralph Lee method versus this 1584. And then when I started to realize that, wait a second, if I calculate incident energy at 105,000 amps, SKM gives me 50 calories. I change that from 105 to 107, and it goes down to 2 calories. And I said, why is that? Well, they're using the Ralph Lee method. The Ralph Lee method doesn't calculate arcing currents. And then I started realizing, well, I understand where Jim's coming from. That the table method it has a whole set of assumptions and a whole set of parameters. You can't mix the table method with the calculation method. And that even in our calculation methods as engineers, we make assumptions, and we're coming up with, we're trying to come up with the most likely value of incident energy. So I get both of those, and I understand the Ralph Lee method. It's a method. But to answer Richard's Curran's question, yeah. Well, okay, Richard. So he said it gave him a high, and I would bet that the reason it gave you a high incident energy is because of you have a transformer, you have a secondary current. Remember, the clearing time is on the primary of the transformer. So you have to do the conversion. In fact, I do this. Oh, this is good stuff. This is what dreams are made of. I did this calculation, Mike. I have an example of a transformer, and I talk about from a safety by design perspective about putting a secondary overcurrent device in the picture. And I showed that whenever you're on the secondary of the overcurrent protective device, your clearing time is going to be based upon the primary overcurrent device. And you have to do, now, how do I pick the primary overcurrent device, fuse or breaker, for a transformer? I don't pick it based upon the full load amps, right? No, it'll never let that transformer energize. I have to put an intentional delay to ride through the inrush current.
And Tom, you're the 70 expert here.
Oh, no.
In my mind, just so everybody knows, National Electric Code Tom is the man, the myth, the legend. I believe there's a table in the National Electric Code, which I don't have one here beside me, believe it or not, that you can oversize protective devices, including fuses, right?
Absolutely.
Like 300%.
Absolutely. You go up to 200. You can go up to 200% on the primary breaker, right? So and so now I have an intentional delay on the primary. So when I have a fault on the secondary and I transpose that to the primary, the way that the Ralph Lee method works is it looks at the bolted fault current and the clearing time of that overcurrent device, and that's what it's based upon. So Richard's example, and he could take a look at it and confirm that the bolted fault current is probably not in the instantaneous region of that medium voltage fuse, because think about a medium voltage fuse. You know, the fuse goes like this, way out here, and then it crosses 0.01 seconds, right? And it's like I don't know. It's like, if I would liken it, you know, your other breakers and whatnot, like a device like this, it's stand up straight, keep your back straight, and you got posture because you're a multi-case circuit breaker and you have an electronic chip. You got to walk like one. You got to keep that back straight. But when you look at a medium voltage fuse, it's like me on the couch, right? It's like just laid way out there, and that adds that delay. That's probably exactly what he's seeing.
And another one, Tom, just because I'm cruel. When I teach classes, some people actually refer to me being the cruel instructor. Not cool.
Cruel.
Right?
Cruella.
Cruel. Yes. There you go. So there's a class where I actually have my attendees draw out time current curves. And one of the things I like to do is say, all right, you got this 100 amp breaker on the secondary of the transformer. We're going to make a curve. We're going to draw it at the higher voltage on that time current curve.
Right.
100 amps is no longer 100 amps, is it? Right.
Exactly right.
It drops down. If it's a 480 to 28, that's 2.3 is a turns ratio.
Yep.
It drops by that value. So now you have to compare all those numbers on the right voltage scale. That's going back to per unit. We're back into the IEEE buff book. I apologize.
Yep. No, you're right. You're absolutely right. Yeah. And it's the transposition. So that secondary. So, and that's why it's really important. Let's go back and I'm going to flip around here. I hope I don't screw everything up. So, where is my Adobe file? There it is. So let's continue on. So you have the fault currents, right? Now, the gaps between conductors, to Richard Corinne's point, the gaps between conductors, 208 to 600 volts, is 6.35 millimeters, or 1/4 of an inch to 3 inches. And then for 601 to 15 kV, it's 3/4 of an inch to 10 inches, or for those of you in Japan and other countries where you use millimeters, I think they use millimeters in Japan and wherever else, it's 19.05 millimeters to 254 millimeters. So 3/4 of an inch to 10 inches, 19.05 millimeters to 254 millimeters. If the gap is outside of that region, you're using other methods like Ralph Lee. And I believe if you go to SKM, EDSA, or Easy Power, they'll tell you what they're using in those applications.
And Tom, I'll add this in. Again, it's broken down by voltages, right? In the 2018 version. In 2002, those gaps, it was just an overall gap. Range that existed, right? They added the voltage separation into this now also. So we're seeing a pattern here that, depending on the system you're working on, if you're in that low voltage, less than 600 volts or less range,
yep,
the calculation is different than if you're in a slightly higher voltage.
I got scared. I thought I lost my SKM key.
Hey, you got to hold on to that. That's expensive.
I'm telling you. In fact, I got the email, I think it was late last year, about updating my license for technical help. So you've got the gaps, and then what else? Working distances greater than or equal to 12 inches. Okay, so 18 inches. So if you want something closer than 12 inches, that's out of the scope of 1584.
Yeah, now I have a note on that one too, Tom, that's a change from 2002. And I'm trying to look up real quick what the change actually is. I wrote did not exist in 2002 with an arrow drawn to that line. Why did that not exist in 2002?
Yeah, I don't see it in 2002 either.
Yeah, that line didn't exist at all.
No.
There was no limitation on working distance.
Yeah. So they're saying greater than 12 inch, and it's probably because that's what we tested to, right? It's about where you put the what do they call those sensors?
The energy sensors.
It's the heat,
or the
thermal whatever. They're like little round discs, but and it's probably based upon what we did there. And there's no limit on fault clearing time. Enclosures tested. All right, so 600 volts, and they have the size of the enclosures that were tested. Enclosure dimensions: maximum height or width of 49 inches. Maximum opening area of 2,401 inches squared. Minimum width: the width of the enclosure should be larger than 4 times the gap between the conductors. So, and then the electrode configurations, they gave that to you. So those are the limitations of this. And the moment you get outside of those limitations, now you're into a different method, because that's not how we tested.
Yes, and per NFPA 70E, other methods are acceptable ultimately.
Exactly.
And that's really the key, right? Is 1584 is one method.
Yes.
In our, it's one tool in our toolbox, right? So that screwdriver, sometimes it may work as a chisel, but other times I do need a chisel, right?
Yep. Now, what you'll notice, based the older version of 70E, the 2018 version, in that annex had the equations for 1584.
Annex D, yes.
Yes, Annex D had the equations. They no longer exist in an informative Annex D. And so, there was a debate on whether or not IEEE wanted to share those equations because they wanted to copyright the equations and all that other good stuff. And that wasn't the issue. The debate at 70E, because I was sitting around on the wall, not on the table. I'm not on 70E, but I'm sitting, I'm sitting on one of those most uncomfortable chairs with my laptop in my lap, and
I can confirm that, Tom, because I was there at the second draft meeting.
That's
on
right.
the other side of the room, looking at you, just shaking my head. So you were there.
That's right. That's right. So and what they did in that discussion was they said that trying to put to I think it was Santiago, the 70E would be a whole nother book with the same thickness because of all the different equations and all of the different iterations, because you had multiple equations for arcing current, you had multiple equations for incident energy, for the different types of I'm just looking at them and see, there were different models for all the different configurations, because you have equations for VCB, VCBB, you have all these different parameters. Like if you have a VCB, you have multiplying factors. If you have VCBB, it's a different factor. You have multiplying factors that are based upon the size. So they could not possibly, without basically taking all of IEEE 1584 and sticking it into the annex, simply put a few equations in. That's the reason why Informative Annex D does not include the equations from IEEE 1584 2018. Not because IEEE is trying to not provide those to anybody. So it's just too complicated. I think they ought to make a movie about it. Call it "It's Complicated."
Well, and I remember in that same discussion, what was really a debate a little bit as to what do we do with the 2002 equations.
Yeah.
Right? Because if you put in the 2018 equations and you get rid of the 2002 equation, are you implying that the 2002 equations are no longer valid?
Right.
That you can't use them, right? And does that mean that the day NFPA 70E took effect, which I forget what date that is.
January 1st, 2018.
Yeah.
2021. I'm sorry. January 1st, 2021.
Right. Yeah. So on that date, does that mean every arc flash calculation we've done using 1584 is now voided and we just throw our hands up? What do you do with that? So there was really, it went on for a long time. What do we do with this annex? Do you put in the new equations? Do you put in both sets of equations? Do you not put any equations? and it was a heated discussion.
Absolutely.
For sure.
Absolutely. And rightfully so, because to sit down and say that what you told people to do back here is wrong, and that then now you have lives at risk. I mean, that's a major thing that you're basically saying. But and there have been IEEE papers, because the basic question, Mike, in my head is, based upon the 1584 2002 and 70E 2018, if I did a calculation of incident energy, how many people have been underdressed because of my calculation? And I think the answer to that is 0, because nobody's been able to produce that. So we came out with a new equations and new calculations. And Jindang, yes, so here's the thing. So that's the debate we're having right now. Is 1584 2002 still valid? And I'm telling you, I'm not an AHJ. I have an opinion. Mike has an opinion. But I can tell you there's two schools of thought. There are those that'll tell you, hey, we have 1584 2018. It's based on extensively more testing. We know more about an arc flash than we did in 2002 because of this additional testing. So 1584 2018 replaces 2002, and you can't and shouldn't do calculations to 2002 anymore. And if you did do equations, you've got to go back and update them. That's one school of thought. There's another school of thought that says, I don't know of anybody who's been underdressed because of my calculations and based on 1584 2002. Is 1584 2018 a more accurate representation? I can argue that it could be. But it doesn't mean that I have to go back and redo all of my calculations from 2002. If I was the owner of a facility and all of my labels are based on 2002, that doesn't mean that if I have an accident today, somebody gets hurt or whatnot, that OSHA is going to come in and say, you didn't update all your calculations, because they would have to show that my calculations were wrong and he dressed appropriately with the appropriate PPE and he was significantly burned beyond or she was significantly injured beyond the level of PPE that the incident energy was higher. Now, he would be hesitant to use 2002 with the horizontal bus. Well, remember, 2002 didn't have anything with a horizontal bus. And if you have a piece of equipment that has a horizontal bus, Richard, I could agree with you. I mean, we know that if you open a piece of equipment and you're staring at the end of the bus, I know for a fact, based upon 2018, that is probably that is going to be a higher incident energy than if you calculated that same example based on 2002. I agree with you 100%. So that, Jindang, is the crux of the debate. When do you have to recalculate? When should you update the study to 2018? When can you simply use 2002? Because there are a lot of examples, Mike, where the 2002 version had a lower incident energy or a higher incident energy, or no, actually, had higher than the 2018. So the worst case is the 2002 version, not the 2018. Right?
Yes.
So that's the issue that you run into, is you can't just blindly say 2018 will give you the worst case, because the arcing currents in 2002 could be lower and put you in a longer clearing time.
Yeah, I was going to say, Tom, I want to bring up 2 points here.
Yeah.
And because I think it fits perfectly. Number one, I am looking at a document from OSHA, and this was in the Electric Power Generation, Transmission, Distribution, Maintenance, and Construction Frequently Asked Questions document. And in this document, the question was asked, what must an employer do to protect employees from hazards posed by flames and electric arcs? And this is April of 2015. OSHA said, number one, assess the workplace to identify employees exposed to hazards from flames and arcs. Makes sense. The second bullet they have, though, is make reasonable estimates of incident energy of any electric arc hazard to which an employee would be exposed. So when I look at this and I read that answer from OSHA, it really gives me the insight of, as you said, we can't predict how that arc is exactly going to work. While we have all these great tools at our fingertips, right? We have the great software programs and we have all these standards that we fall back to rely on. In the end, when that arc happens, I can't tell you exactly what that energy is going to be. I can make a reasonable estimate using the tools that are in front of me.
Right.
And from that estimate, we know, like you were saying, if you use 2002 equations and you dressed for those equations, how many people were injured?
Yeah.
How many people sustained those arcs? And like you said, I'm not aware of any instances where that's happened. So, the 2002 equations in my mind are still a valid equation to use. The same as Ralph Lee from the 80s is also a valid method to estimate that energy because we don't fully understand how these arcs are going to work. The other thing I want to bring up, jumping back to 1584, I want to go to Annex C, as in Charlie, in 2018. And this is examples on how to determine the incident energy for different equipment types. And what I find really interesting here, so 2002, we didn't consider this vertical bus, horizontal, all that stuff, right? But they say that an arc flash may occur behind a circuit breaker compartment in switchgear. With the circuit breaker could be racked in, but not secured. Or there could be no circuit breaker present at all. Or the circuit breaker fails, it was racked in, and that's still where the arc flash occurs. And the energy breaker in the cell, not in the cell, is going to be significantly different when you look at the energy coming out of that cell.
That's right. Yeah.
So it is an estimate, right? Because
Yep.
I don't know how we were talking about all the different old and fault currents you have to take into consideration. Can you imagine if we had to do studies and now write the energy calculation based off of the situation that use the workers actually in, breaker out, utilized, not utilized.
So Mike, that's so that's the thing, and some engineers that I've talked to, and to Santiago's point, I think it was Santiago. He says now, I mean, someone could present right now do a study with IEEE 1584 2002 and another one in 2018. So what I have actually seen studies done for customers, because I've had people call me and say, would you believe that this facility wants me to do a calculation with both the 2002 and the 2018 and take the higher of the two? So he's doing 2 studies for that system. And that's so here's the thing. Knowing how Dr. Lee came up with that lower number of arcing current, the 85%, you think about it, he had a bunch of data points. He had a bunch of data points. I don't know if I can do this, but let's say that he had this going on up here in the top, and he had a data point here, a data point here, a data point here, a data point here. And then over here, he has a data point here, data point here, data point here, data point here, data point here. And up here, he has a data point, data point, data point, data point. What he did was he drew a line along the top, and he calculated that for the 2002 version. And then what he did was he said, I'm just going to take 85% of all these numbers, and I'm going to draw this line. And there was, maybe there was one outlier that was way down here, close to that 80% line, okay, 85% line. that he had to encompass. So that 85% is artificially low, right? And when he finally came up with an actual equation, he was able to get it a little closer to where the data points were. So if you did use 2002, in many cases, you might use the 2002 version and have a higher incident energy value. And then in the 2018, it might be less. And then the argument would be, which one do you use? I could argue I would use the 2018 and just be done with it because it's the latest version of the document. But if I'm in a facility that's already labeled with 2002, now the debate comes up, do you use, which one do you use? And so Ryan Jackson says if an incident happens and your calculations were based on an older standard, you would have a bad day in court. But what if I'm on the stand and I can say, look, the 2002 version calculated 40 calories. The 2018 calculated 20 calories. I dressed my guy in 40 calories. I think that'd be a good day in court, not a bad day. But if the 2018 version calculated 40 calories and the 2002 calculated 20, now it's a bad day in court. So it's an interesting debate and discussion, and I think it has to be had on a case-by-case basis. I think if you go to Ryan's point, if you just simply said, look, I'm going to use the 2018 from here on in, I might have a system that's labeled in 2002, but I'm going to use the 2018 because that's the latest for the rest of my equipment. And then as we go and progress, I'm going to update things as I make, because remember, what does 70E require? Every 5 years, you've got to update your calculations. But then the debate is, in 5 years, do I have to update it to the 2018? And my answer to that is no. Now, I might be wrong. I might be completely wrong, and I might be on the stand having to defend that, and I wouldn't want to be on the stand having to defend that position. But it just seems to me that it'd be probably in some cases a very huge effort and costly, and then you have to weigh the benefit of it.
Yeah. So Tom, you hit on one of my pet peeves with arc flash studies, and I know we're friends, so I can bring this up.
Yeah,
I'm going to actually disagree with you there just a little bit, and that's the great part of this, right? That
right.
We can disagree.
Because you know what I can do, Mike?
You just mute me.
Here, Mike is gone. Thank you, everybody, for joining. It's been a great discussion with Mike.
I love it. Okay, so since we're live, this is the great part of it. 70E and their 5-year arc flash, as you said, recalculation.
Yeah.
Is that the wording? I want to make sure I quote you properly there.
No, it doesn't say. It's what it says is. It says, in fact, what it says is if your system changes. It doesn't say if the methods change. It says if the system. Now, if my system did not change, I got to find it. Ryan Jackson will probably be able to help us find this. It's probably in 110.
Okay, I found it. It is 130. We're in 130.5H. And here's what I want to say. I want to read this verbatim. The method of calculating the data to support the information for the label shall be documented. The data shall be reviewed for accuracy at intervals not to exceed 5 years. Where the review of the data identifies a change that renders the label inaccurate, the label shall be updated. So there's actually not a requirement to re-perform your arc flash analysis, as in do all the calculations every 5 years.
Right.
You need to review it for accuracy, right? So in theory,
hold on. It says where the review of the data identifies a change. My data isn't changing. My data is the same. It's my calculation method that has changed. So and I don't know what the right answer. I mean, I think where you run the risk is when you have that HCB or the VCBB, where your incident energy in the 2018 puts a little bit higher. Panel boards, if you look at panel boards and their construction, I think you're going to get a higher incident energy on the 2002 version than you will in the 2018. But it all depends on the clearing time and the arcing currents. So
it does.
Yeah, and to Ryan's point, you've got lawsuits, you've got civil lawsuits, and Matthew says, any day in court is a bad day, and I don't ever want to be in court. I don't want anybody ever quoting me. But I've heard this debate multiple times, and I can tell you, what I can tell you is both sides of that argument. One saying that, hey, my data's not changing, and I've heard this argument before, and I agree with you, and I agree with the other side as well, saying, but all of the equations change.
Yeah.
And the last thing you want is to have this debate in front of a lawyer. So
right.
I think
the thing is, Tom, honestly, and I wasn't doing arc flash studies back when 2002 came out. But from what I've gathered from all my colleagues is when IEEE 1584 2002 came out, kind of the same debate happened. Do we switch from the Ralph Lee to this 1584 document and these equations that are a change? And we're human; we don't like changes, right? Do you do that? And I think over time, as people discussed this more, read the documents more, talked to different people, it became more and more accepted. And I think that's what you're going to see here with 2018 is I think there are still going to be firms that want to use the 2002 equations. Yeah. But I think as we progress through time here, more and more of industry is going to switch to the 2018, and the 2002 will just kind of fade off into the distance, right?
Yeah. And so then the other issue, Mike, is what happens if you have 150,000 amps and you use the Ralph Lee method, and so if I was on the stand and I calculated 8 calories because I used the Ralph Lee method at this service entrance equipment, and I know as an engineer that the arcing current is going to be much less, and I know as an engineer that my instant energy is going to be maybe 40 or 60 calories, do I label it with the Ralph Lee method? It's right in 70E that I can do that. Or do I say, no, I'm going to use my engineering judgment and I'm going to do something a little different. That's the key. Mm-hmm. I mean, it's an engineering judgment call. And if I was on the stand and they said, Mr. Dimitrovich, how did you label that? Well, I didn't use the Ralph Lee method. I used this method. And if they said, that's not recognized in 70E. And I would say, well, if I use the recognized method in 70E, it'll give me 6 calories, not the 30 calories that I labeled it. You know what I'm saying? But I think your point earlier, this is an estimate of incident energy. And if you state your assumptions, and it might be that, hey, look, I did an analysis, 2002 versus 2018. That piece of equipment has a higher incident energy. The label that's on it is higher than what I did calculated for the 2018. I'm going to leave that label on it. I don't think there's anything wrong with that. But if you calculated it in 2018 and your new number is much higher, then I think you've got to do a change. Either way, you should look at it.
Yes. Yeah. If you've done those calculations and you've done the comparison, I think you have to look at it from an ethical view, right? That I need to report that higher energy so that those workers are going to be protected. I mean, honestly, there's a difference, and I'm glad we're talking about this. So, in 1584, and up until yesterday, I had not really picked up on this, and the light bulb hadn't come on for me. There's a definition of a qualified person in 1584 that is different than the definition of 70E or even OSHA or Z462 and all those other standards, right? And that qualified person, it says a person who performs arc flash hazard calculations by using skills and knowledge related to the construction and operation of the electrical equipment and installations, and has experience in power system studies and arc flash hazard analysis. So you're looking for a qualified person, somebody who has that skills, knowledge, experience to make these determinations as to what instant energy should go on that label, because your qualified worker for 70E, your electrical qualified worker,
right,
is not necessarily an expert in all these calculations we're talking about.
No, yeah, you're absolutely right. You're absolutely right. And if it's a non-labeled environment, they'll use the tables as long as they're within the parameters of the tables. If they're not, if they're outside of the parameters of the tables, then they're going to have to do a little calculation. But NHZX Boy says calculate too high, and he brings up a good point. That let's say you put somebody into a 40 cal outfit, and he passes out due to heat exhaustion. Okay, now what I would say is those outfits have built-in fans, and we had Scott Margolin here, and he talked about all the different personal protective equipment and whatnot. I mean, they have fans, they have all kinds of stuff for personal protective equipment. You know, if they can't, if the suit's too heavy, then you got to look at your limitations. But he raises a good point that you don't want to put your electrical worker in too high of a personal protective equipment, because there are other hazards associated with the clumsiness of it and all this other good stuff.
Yeah, and I'm gonna bring up this, Tom. So I have the old version 70E, right? And we have the matrix or the pyramid on there, right?
Yep.
What's at the bottom of the pyramid?
PPE.
That's the probably easiest thing to do, I guess, in most situations, but it's also the least effective.
Absolutely. Last
solution.
Resort. Santiago's pointed it out. The PPE is the last step in the hierarchy of eliminating a hazard. So
my question here is, I guess we do all these calculations, and we're engineers. We love these calculations, right? But is the point to really identify the hazard so we can choose the PPE? Or is there a better option? We're doing these calculations to identify those more dangerous, that's a technical term, more dangerous locations.
Yeah.
And now we can talk about some other engineered solutions
yes.
to either move the employee, move the arc, reduce that energy, some other method.
Right. Well, Russ Seyfried was saying we got to get people outside of the arc flash boundary and get them working outside. You've got arc resistant equipment. You can put arc reduction maintenance switch technology in to reduce it, to get people into light personal protective equipment. We shouldn't have to be thinking about those big energy events, because as long as we can estimate the arcing currents and things like that, we can put the technologies in place to identify, just like you said, you identify the hazardous areas in the power distribution system, and then you design the system to provide a safer installation. I like the way you think.
Exactly. Let me give everybody a scenario out there. With everything we've been talking, we say higher fault current makes those turn devices clear faster, right? We know that from the time current curve. So in application, my fault current is going to be fixed, right? I can't just go change that and make it higher somehow, right? So what do I have to do? I have to now lower my settings if I want to clear the fault instantaneously, which we know that can't happen due to coordination issues.
Right.
Well, how do I make a breaker clear a fault faster and still have the same current? I mean, think of technology like ZSI. ZSI clears that fault instantaneously, and it's not dependent on a level or a magnitude of fault current once it hits that minimum threshold.
Right. And arc quenching technologies, same way, right?
Absolutely.
But you know, I just can't ignore Matthew Hermanson.
We're
Dr.
not
Fauci
really done
says,
go there, are we?
if one suit is good, then double suiting should be better. So yes, you need to wear 2 suits. Oh my gosh.
Wait a minute. We need to talk to Scott about layering now.
Yes, I gotta go. This is
Yeah.
So
can we call Scott up and see if 240 calorie suits equals, I don't know, 100 calories?
we're gonna have to do that. 240 calories. So now let's take the discussion real quick over to this. So I have this spreadsheet that basically looks at the bolted fault currents, and I modeled the 2018 version equations. I have a maximum and a minimum arcing current. And then I have all the different parameters that we just talked about: the working distance, the gaps, the height, the width, and the depth of the enclosures. So some of these parameters will impact arcing current. Some of them will impact the arc flash, and some of them impact arcing current and arc flash. So if we just focus on the 10,000 amps, now here's a good example. My maximum arcing current is 8,002, right? Or 8,000 and 8.02 kiloamps. If I
8,020.
Yeah, 8,020. If I multiplied that by 0.85, the minimum arcing current is 6,817, but the calculated value based upon 2018 puts it at 7,007. So if 6,817 puts you into the short time delay and 7,000 puts you into the instantaneous, the 2002 version would be worst. Worst case. Now, let's just let's modify some things. Working distance. I'm not a millimeter to inches person. So what's 457.2 millimeters? Somebody out there, Matthew, Santiago, Boy, Richard, 457.2 working distance. That's 18 inches, I believe.
I believe so, yes.
Okay, so what if I change that to, I'm going to do millimeters, inches to millimeters. This is 18 inches. Okay, I'm going to double the distance. Forget it. I'm going to make this 900. 900 millimeters working distance. Let's watch what the arcing currents do for, and watch the 8.02 and the 7.07. When I hit enter, 8.02 didn't change, 7.07 didn't change, but my incident energy values went down. So if I go back to 457, my incident energy at 0.01 seconds is 0.19. 0.19 becomes 0.06. Tamaki, thank you. and Ryan. Geez, oh man. So if I double the distance of working distance, my what is double? What's 457.2? 457.2 2 times is 914.4.
Yep.
Down to 0.05, from 0.19 to 0.05. So if I doubled my working distance, my instant energy significantly is reduced. Okay. Now, what about the gap in the electrodes? I'm going to increase the gap. I'm going to double the gap to 50 millimeters. I changed the arcing current. So let's go back to 25. 8.02, 8 kiloamps. If I go to 50, 7.66. I lowered the arcing current. Why? I added more impedance into the circuit, right? Because it's more of a gap. There's more gap. There's more ionized gases and whatnot. So there's more impedance. So, and changing the arcing current will also change the incident energy. Okay, so gap impacts arcing current. Working distance does not. What about height of the enclosure? What do you think? So, Ryan Jackson and Tamaki and Matthew. If I double the height, will arcing current change? while I calculate, I'm going to change the height. 914.4 times 2 is 1,828. What do you guys think? Will it double? Or will the arcing current change? Go up or down or stay the same? I should have my what do you call it? My Mentimeter. That's what I need to do. Tamaki says increase. All right, so we're going to put the number in. 1, 8, and Tamaki's the only brave one out there. Everybody else is like, well, I'm not saying anything because I have no clue.
I'm going to say it doesn't increase or decrease the arcing current at all.
Okay, you're going to say
it changes the energy.
It changes. You're going to say it changes the energy. Tamaki, are you talking? Well, I missed the first part of the question. Oh, bummer. It wasn't a 2-part question.
Likely excuse.
Yeah, they're still calculating millimeters to inches. 1,828. It doesn't change the arcing current. It does change the incident energy, and it decreases the incident energy. So let's go back. 1828. I have 0.16 to 0.19. So the smaller the enclosure, I change the incident energy to the worker, but I don't change the arcing current. And that's critical because the arcing current is going to help me establish the clearing time. And I know that if I change the gap in electrodes, I'm going to change the arcing current. But if I have these different size enclosures, let's try width. Let's do 1,000 millimeter width. I have 0.19, I go to 0.18, but my arcing current did not change.
And that really, while you're doing that, Tom, that makes perfect sense. Just giving it a common sense gut check, honestly.
Yeah.
So changing the box isn't going to have an effect on the impedance of the circuit. So current should still be relatively the same. But energy is going to be projected out in 3 dimensions. And if you narrow that projection area that it can come out of, that energy is going to be more focused, right? So think about a mag light where you turn the front and the beam of light actually gets wider. And when it gets wider, it dims. And if you decrease it down, it gets stronger, right? That we're not actually changing the brightness of the light bulb. It's still the same number of lumens.
Yep.
But it's being focused more. So it makes perfect sense to say if I change the box size, my energy should change, but not my current.
You know what? And Richard Curran gave me a great idea.
Oh.
A firecracker in a tin can versus a firecracker in a trash can.
Can we move this video outside, Tom? Let's do a live test.
Oh man, I'm telling you. And then I got to look up the Hodder-Wallace procedure.
Ooh, yeah.
Santiago, you're throwing some new stuff at me there. I have an objective only to protect against arc flash, but to have a great impact on instant energy. That's right. Matthew's driving and he's listening. That's cool. And from what? Well, hopefully he's not typing and driving. Hope you're not at a red light. Jeez.
That no, he's using that text. Voice
that's right. You can talk. Siri. Electrical time. Hi, Tom. Steve Cavaleris. Excellent, Steve. Is it available for download? So here's what we do, Steve. You got to go to thomasdimitrovich.com. If you register, it's not paid. If you, what do they call that? Not register, but if you subscribe on my website and you give me your information and you check the box that you want to be I call it gold member. If you want to be a gold member, then I'll get you on that list and you'll have access to that. I like to keep track because this is a training tool. This is an education tool. This is not a tool to use in any type of environment other than education. So we know that height, width, and depth will change the incident energy. The firecracker in the can, I love that. The gap between electrodes will change the arcing current. Now, VCB, VCBB. So right now, this is VCBB. This is a barrier. If I do VCB, what do you think the arcing current? Will arcing current change?
Ooh.
That's a good question. I can't remember to tell you the truth.
Oh. Ooh.
All right, we're going to do it. We're going to look at arcing current.
Nobody else will answer. I'll take the chance, Tom, and say yes.
Okay, you're going to say yes. All right. And here's, but let's think about this before we do this. Let's think about it. You have VCBB, right? So you have an enclosure like this, and then you have a barrier at the bottom, right? And you've got this is my Keith Laughlin special pen. So you have your arc, you have your space between the end getting closer. So what I'm thinking, Mike, I'm thinking that my arcing current might go down in VCBB. I don't know if that's true. I can't remember, because I'm thinking that you have lower space and you have probably less impedance.
Yeah, because I'm thinking you have ionized air that's going to, in essence, not be trapped completely, but it's going to build up. And as it ionizes, more resistance impedance should go down.
Oh, I got it backwards. VCBB. Oh. So this is VCBB. Yeah. So right now I've got 8.02 arcing current. If I move it away, I have more space, to your point, and that's what it was. So I have more space. I have ionized gas. It'll probably lower the arcing current. I would think it would go up if we decrease spacing. You're right, Ryan. So that's what I thought is right now VCBB. This is a theory. You know what we call this in the engineering world? This is theory, and then we're going to test it and verify our theory. But the theory is the closer you are, the higher the impedance of the arc, the lower the current. The further you are away, the lower the the further you are away, the lower the impedance, the higher the arcing current. We're going to try it. I don't know. I'm just going to hit it.
Okay, now put the spreadsheet back up on the screen, though.
Oh, yeah.
We can't see,
no.
Tom.
Oh, wow, you should see this. Holy cow. I can't believe it, Mike. Look at that. Oh, my gosh. Let's move on to the next topic.
I've never seen something that amazing. I can't do it again, Tom. We saw it once. Move on.
Okay. I want you to get the same effect that I got. So if I type in VCB, as in Bob, not VCBB, my arcing current goes down. So
because I have no barrier.
Yes, because this is still hypothesis. You don't get to call this theory yet. It's still a hypothesis. See that? You're right.
Oh,
evidence. So the further I am away, the lower the impedance, because VCB, I'm further away, my arcing currents go down because, or did they go down? Yeah, they did. VCBB, my arcing current went up, so I have less impedance. The closer I am, the less impedance. The further off I am, I have more space, more airspace, more gap. Then I have a higher impedance when I further go away.
So lower current. Yep.
Lower current. All right. Man.
So we made a hypothesis. We tested it.
That's right.
Now it can be a theory.
Now it can be a theory or a theorem.
Theorem?
I don't know. It's all hypothetical. No, it's all whatever. Okay, so we know the bus. Now let's try HCB. What do you think HCB is going to do? Ryan Jackson and NHZX boy and Tamaki.
You know, we need a little polling program.
You know what?
And everybody can polls, and then we say it's completely anonymous, but then you show everybody's names, their votes. Right?
Well, that's right. Well, put it this way: if I'm putting myself out there and you're putting yourself out there, then they got to put themselves out there too. Okay, I'm gonna hit enter, and we're gonna see what happens with HCB. My guess, it's gonna go up. It's gonna go down. And Ryan says I was laughing. I didn't hear the question. Bull crap. Yeah. Okay, so HCB, my arcing current 7.64 VCB versus HCB.
Uh,
They're pretty close.
Okay.
What about what's the other one? There's VOC.
All right. I always forget the
HOA.
HOA. Yep.
See, I didn't look at my values. I didn't. My calculator doesn't include the HOA. I do VCB. Whoops. VCBB. And then I did HCB. So HCB has a lower arcing current than VCBB. HCB has a higher arcing current than VCB. No, less than. So HCB gives me a lower arcing current, and then VCB, and then VCBB. So it sort of gives you the comparison, and really it's about the ionization, and it's based upon testing. Now, we know that if I change voltage, if I change 480 to 208, we know the arcing currents are going to go down considerably because my voltage has changed. And I'll tell you, that's the harder part from a overcurrent protective device perspective. The arcing currents at 208, because they're so much lower, and my trip curve. So think about this. A circuit breaker, a 600 volt circuit breaker or a 600 volt fuse can be used on a 208 volt system. The trip curve is going to be the same. Even in some of my breakers, I'll have a 208 volt rated breaker, but the trip curve is not changing because it's about current. And so at the lower voltage, with the lower arcing currents, I can have higher incident energy on some of these breakers. Make sense? It does to me. So that's all that matters.
Wait a minute, Tom. Say that one more time. At a lower voltage.
Because the trip curve is staying the same, because my trip curve is staying the same, my arcing currents are going lower for the lower voltage. I could have a chance of having a higher incident energy at a lower voltage than I would at the higher voltage, because my arcing currents are higher, because it's a 600 volt rated fuse or a 480 volt rated breaker, and I'm applying it at 208. My arcing currents at 208 are going to be significantly lower than at 480, so I could have a longer clearing time on my arcing currents.
Makes perfect sense after you said it again, and I thought through it. And I'm going to make a hypothesis here that would be why would you have a arcing current that's going to be less at the lower voltages?
So here's the thing: your bolted fault currents are going to go higher at the lower voltages. Your point, right?
Right. And so here's my thought process on that.
You're right.
Tell me if I'm out of my mind here.
Yep.
That would be because that ionized gases, right, that are being produced during the arc, that is going to be a function of the current flowing, right?
Yep.
And because I'm at a lower, and really that's tied into power, not current. Let's fix this, right? The ionized gas creation is really power, which is VI.
Yes.
So at the lower voltage, I don't have as much power because I don't have the voltage, even for the same current.
Right.
I create less ionized gas. I have a higher resistance. That arcing current never can increase as much. It's all tied into power, not current. And the entire time here, we've been talking about current. Except for, tying this all back, we said 2018 had broken some of the range of model into voltage levels now, not just relying on current. So is it really a function of power?
But hold on. Okay. So I get it now. I get what you're saying. And we're okay. Okay. So if I look at this spreadsheet and we're over time, we're over 2 hours. So we're gonna have to close on this because I gotta pack. I'm driving tomorrow. So anyway, although I love this discussion. Here's the incident energy. Let's just look at this number here. Okay, at 0.03 seconds, typical molded case circuit breaker, right? 480 volts. My incident energy is 0.56, and to your point, what you're saying is that the lower voltage will give you a lower energy because you're looking at it as energy, okay, as power. And you're right. But I'm going to explain my point here in a second. So when I go to 208, I go from 0.56 to 0.32. So your statement is 100% accurate, and I agree with it. But here's the difference. When you think about the trip curve, if at 480 volts, my lower arcing current is 7 kiloamps, okay? Let's say that 7 kiloamps is in the instantaneous region of my breaker, but 6,000 amps is going to be in the short time delay. So I'm going to go from 0.03 to 0.07. Okay, if it's less than 7,000 amps, I'm going to have a clearing time of 0.07 seconds on this overcurrent device. Trip curve doesn't change whether it's a 480 volt or if it's 208 volts. Now, let's lower this to 208. My arcing current went to 4.31. My incident energy went from 0.32 or went to 0.75. Okay, and let's take it back to 480. 0.75 at 480 was 0.56. So I lowered my arcing current, but I have a longer clearing time, so my incident energy went up. That was my point. And the reason I say that was because what we were doing was we created a tool for 24067. And what I can say is that if I'm downstream of my 1200 amp fuse, okay? So if I come to this table here and I say I'm going to look at 1200 amps, and I want a fuse. I want a fuse type. I'm going to select all and a day. I got too many filters on. Here's my fuses. Okay, so I'm at a 1200 amp fuse. If I'm at a 1200 amp fuse, I know that my instantaneous is around 12,600. Or no, 17,800. Any arcing current greater than 17,800. Okay? Any arcing current greater than 17,800, I'm going to be in the current limiting region of that fuse. So, when I get to my minimum arcing currents for a 480 volt system, I need at least 25,000 amps of bolted fault current value. Any bolted fault current value greater than that, and I'm going to be clearing in the instantaneous region, let alone the 0.07 seconds of 24067, right? Mm-hmm. Now, watch what happens at 208. So I said 17,800 or whatever, right? Now, 17,000 amps. I need at least 58,000 amps. Okay, because the arcing currents are lower, that same trip curve will take longer to trip at 208 volts with a lower fault current. But, and which is what I thought the point you were making earlier, when you have 208 volts, your fault currents are much higher because you're at the lower voltage. If you put a transformer in and you went down to 480, or if you had if you didn't have the transformer in, if you had 480, I mean, just think about the principles. If you had a 480 to 208, the fault current at the 208 side is greater than the fault current on the primary side because it's at a higher voltage. So my fault currents typically on 208 volt systems are higher anyway. And so but it really shows you the dynamics between fault current, arcing current, and clearing time. And understanding what impacts all of that helps you with that whole picture.
Yes. Wow.
So you said on LinkedIn this morning, you said we're going to need 3 hours, and here we are at 2 hours and 12 minutes, and I think we need to. And Santiago, would GFCI, FCI, or other equivalent protection devices be easier to implement at the lower voltages and also reduce AFCIs and GFCIs? That's 120 volts. They don't address what we're talking about here. You would need arc reduction maintenance switches. You would need instantaneous. You could use zone selective interlocking, arc quenchers. And I think what we should do, Mike, is schedule another program where we talk about the technologies that and how they can impact incident energy, and talk about the trigger set points and all that great stuff.
Yeah, I think we should. Can I get? I want to get one more thing in this conversation. I know you said you're driving tomorrow. And
no, go ahead. What's up?
So one other huge change that we haven't touched upon yet is on this lower voltage perspective, and that is a statement that existed before about energy needed not to be considered for a 208 volt system at less than 125 kA transformer. Right, the smaller systems. We didn't even touch that here.
No.
That now it's based on voltage and a fault current less than 2,000 amps.
Yes. So now remember the was so 1584 2002 had the transformer size in it.
Yes.
Okay. Right. So
and it was in 9.3.2.
Okay, so what they did in this, when they were running the tests, they kept lowering the fault current. And what you'll notice is it says 2,000 amps is the floor, but what does it say? It's not likely to sustain itself. Dr. Lee will not say it will not sustain. I mean, there are a lot of people that tried to get him to say that. He would not say it. He said it's not likely to. So now, this is for a 3-phase system, right? Within these parameters, what's not here is a single-phase system, and that's the testing that we are doing right now. Last week, all week, we had to virtually do this. We were dialed in. Dr. Lee, myself, and a bunch of others. They're just shooting over and over and over in the lab down at the Busman facility. I can't share any results because it's still not conclusive, and it's all, we just can't make any statements with regard to what we're finding in the 120 volt side. But they're doing that calculation. And Dr. Lee also has a theory. He has a theory that, so we're doing the testing at 120 volt. And we're also doing testing to support his theory for DC. So we're doing DC arc flash testing as well. And we're going to try to come up with equations for the DC side, because right now we use the Dan-Doan method, which is extremely conservative and putting very high incident energy. So what Dr. Lee is trying to do is say, look, can we use the 1584 equations with some modifications to calculate DC? And also on the 120 volt side and 240 volt side, single phase side of the business, can we establish a floor to say, just like we have in the 3-phase, 2,000 amps, like to your point, can we do something for the single phase stuff to say, can an arc sustain itself? And the trigger that we're using for sustaining itself is 3 cycles. So what we're doing is we're hitting it and we're recording the clearing time, and the lab can get very accurate, and they'll tell us how many milliseconds, and then if we don't get an arc to sustain, we try it again. I can't remember, it's 4 or 5 times in a row we need to get the same result, and then we say, okay, it did not sustain itself. And he's got he'll probably do an IEEE paper, and you'll have to come to Electrical Safety Workshop to see it. But But the testing that we're doing is we're trying to figure out do we have to worry about 120 volts? Do we not have to worry about 120 volts? What about 240 volts? At what fault current values below which is it not likely to sustain itself?
Yes, not likely.
And we have another week planned. So I think we're going to complete all of the testing in the next one, which is I think week after next, we're going to do another week of testing. And then Dr. Lee will go back, do his math, come up with his equations and his presentations, and he'll probably deliver it at the electrical safety workshop this year or next year. So I'm hoping that people go down there and see that and see what the results are at that event
in Jacksonville, Florida.
And look at this, we've received 100 messages today.
Awesome.
That's great activity. So this was in Jacksonville, Florida. So this was an awesome discussion, Mike. I really enjoyed this discussion.
Yeah, you know, Tom, I always enjoy coming on here with you. I love this format, right? That we didn't really come with a lot of presented material, slides, pictures, right? We came here and said, hey, let's just talk. Yeah. And let's see where the conversation goes and kind of, figure it out as we go. And it sounds like, Ryan and Santiago and everybody else has had fun with this one. So,
yeah. And they all hung in there.
Yeah. And I think our emails are going to be blowing up over the next few days going, Mike, Tom, you missed this, you missed that. Why didn't you talk about this? And I think we're going to have to come back for a part 2, a part 3, and we'll continue doing it. So
yeah, we will. And thanks for Ryan gave us more beer money. You're the man, Ryan. I don't know what I'd do without you, babe. Don't know where I'd be. You're not just another streamer. You're everything to me. Cool beans.
Wow, you do poetry live on the air. I didn't know that one, Tom.
That's a song. Oh, man. All right. So, listen, we're going to have to shut this one down. I got to go pack. I'm going to North Carolina. My wife and I are, so we're going to have some fun.
Enjoy for sure.
So Rob, thank you. Richard Curran, Ryan Jackson. Oh man, who else we had up here? Santiago. I don't know if we got James Smith and Bowie, and
we had a mismatch of characters.
Sure did. It was good. It was a lot of fun. Mathur Abbasi still hanging in there. You're the man, Mathur. Thank you. All right. Well, Mike, thank you very much. Appreciate you coming back again, and I'm looking forward to the next one. And Jinzang, thank you very much. Richard Curran. We're going to have to come down. Yeah, we're going to come down to, I'm going down to Charlotte, actually. Excellent. Awesome. All right. And don't forget to subscribe to my YouTube channel. Check out www.thomasdimitrovich.com. I put my schedule up there. If you subscribe there and say you want to be a gold member, then I'll get you into, I'll get you some access to some materials that not everybody has. And I'd like to just keep that, I'd like to keep that tight. So you become a part of the family. You know what I'm saying?
Yes.
So.
And reminder, www.eaton.com/electrical worker training is our training group that we have lots of good classes. If you look at the in-person section, Tom, IPSA, Industrial Power Systems Analysis 1, is how to do all of your short circuit calculations to determine that voltage fault current, right? We looked at load flow and some other things too.
Yep.
And then IPSA 2, Industrial Power Systems Analysis 2, is coordination and arc flash calculations. They are in-person classes. As soon as we get some restrictions lifted, we're going to start having in-person classes again, open enrollment. And I guarantee you there's going to be some e-learning, remote instruction that's going to be hitting the website here to watch out for. So if anybody hasn't been there to check out the website, you have it scrolling at the bottom of the page every single time you do these tech talks. I love it, Tom.
Absolutely,
and there's even a free promo code I think we've given on every other one, right?
That's right.
Eaton Tech Talk.
Eaton Tech Talk. Don't lose the #, Eaton Tech Talk. That's your promo code, 10% discount. Act now. Crazy Tommy's going insane. All right. So thanks, everybody. Thanks, Tamaki, for dialing in and hanging in there. Ryan Jackson, all you guys and gals out there. So thank you very much. And we're going to sign off. So take care, stay safe, and stay healthy, all that jazz. All right. Thank you, Michael. I'm going to sign off here and hang in there for a second. See you guys next Tuesday. Signing off.